Okay. Hello, everyone, and welcome to ECE 350. So, for those of you who haven't attended any live events on Teams, so this is the framework we're going to use, at least for now. If you have any questions, please use the Q&A to ask your questions. When you post the question, I'm going to see the question, and I will basically respond and publish the questions that I get as time permits. So there is one thing to note is that there's a 20 minutes difference from when I say something until you hear it. So there might be some delays when you ask your questions until when I see it or when you hear my answer. Let's put it that way. So bear that in mind. Okay, so without any further details, let's get into it. So today we're going to talk about how things work in ECE 350. If we have time, we'll talk about what is a real-time system, what is an operating system, and what makes operating systems, especially real-time operating systems, exciting and interesting. Okay, so the course website is up and running. So I assume those of you who are here, you found the link on the website. Just to walk you through it, here's the website. There are information that you need. The most important piece of information, or the most important piece of the website, part of the website, is this is schedule. This is definitely tentative. Now it has different columns. So the weeks, the days, that those are basically trivial. The content is where I post the slides and links to the lectures, and once it's done, the link to the recordings. The readings are basically what you might want to read for that lecture or that tutorial, and the events are the deadlines. So one thing to note is that this schedule includes Fridays, which is our tutorial sessions day. So if there is a link for tutorial, that means that that Friday will have a tutorial. If there is no link, it means that there won't be any tutorial. So that's how you might want to know if there are tutorials or if they're not. Also, the makeup sessions are marked. So for instance, on Friday, February 11th, we have a makeup session. So there's a link for that lecture in here. The same link that you used to join this live stream, you can use it after the live stream ends to watch the recording. I'll try to also upload the recording on YouTube, but if it's not there, you definitely can use the Teams. Or if there is any delay, you can use the Teams to watch the lecture. Another piece of the website that is important is basically this resources section. So here I have a couple of previous exams from SE 350 and a bunch of Berkeley exams, a lot of them, more than 20, 30 different samples. So whoever wants to prepare for the exam, they can use these sample questions. Lastly, the FAQ section lays out all the policies, all the important policies. I'm going to walk you through some of them, in the lectures and in slides, but it's a quick read. So just make sure that you read this for the policies. Okay, let's move on. Okay, so the course on Piazza is available, and then there is this anonymous feedback form that you can use to give me any feedback you want. So this feedback form will be available during the term. If you have positive or negative feedback, definitely use it. To not make me depressed, try to put some positive stuff as well. But joking aside, the positive stuff that you put there is also good for you, because I might get only negative comments for people who don't like something in the course. And that's something that people are complaining about might be something that you like. And if I just get the negative ones, then I might change that part that you like without knowing that you like it. So use this feedback form to communicate with me anonymously. That's what I'm basically saying. For the time being, the course the lectures at least will be offered online. This might change or might not. Even if we go to online setting, we might still use if we go to in-person lectures, we might still have the lectures delivered online. I have to verify and finalize that. But for the time being, we're going to be online. If you want to book appointments with me or the lab instructor or the TAs, you can use the website. So switching back to the website again. Here under my name, there is a book appointment here. This link doesn't work right now. Unfortunately, I didn't get a chance to set it up, but soon this link will be functional. So if you have if you want to set up an appointment with me or with the lab instructor or the TAs, you can use these links to make appointments. Okay, going back, lab tutorials would also be online for the time being, but that might change if we move up to in-person setting. Okay, so I am Sayed Majid Zahiri. That's kind of late, 7 minutes into the lecture, introducing myself. So I am Sayed Majid Zahiri. I have been a professor here at U Waterloo ECE for now more than 3 years. I joined 2018. I have been teaching SE 350, EC 350, another game theory course, and I probably will be teaching distributed systems next year. Your lab instructor is my master student, Arvind. Will be helping you with the labs, and we have 2 graduate TAs. Their information is here, and you can email them. I mean, hopefully you don't need to, but if you need to, their email addresses are here. The main textbook for the course is is the operating systems principles and practice. Your library has this book. You probably won't need it because everything is included in the lectures, but I think it's a good practice to read the book nevertheless. There are 2 optional references: the operating system 3 easy pieces. This one is freely available online, and I think this is the reference that is used by CS 350. We also use it sometimes. There are references to this in your optional readings, and also the lab 1, the first part of the lab, you will have to read a section from this book to be able to implement your labs. Then there is the operating system concepts, the 10th edition, which is again available in library. I am assuming that you know certain things from ECE 252, so I won't excuse me, I won't emphasize or I don't go deep into these, I might reintroduce you to them, but probably very in a shallow way. Including file systems API, process, what is a process, what is a thread, how you can do inter-process communication. I got a question, I will answer that later. I'm assuming that you know networking. I assume that you know what concurrency is and what deadlocks are and how you can avoid them, how you can detect them. So I'm assuming that you know all of that from ECE 252. If you don't, definitely go ahead and refresh your memory on those topics. Okay, so what is ECE 350 about? We're going to talk about design principles that have been developed in the past 50, 60 years or so. We're going to talk about trade-offs between these designs and the efficient implementation of those designs and those concepts. So why should you take ECE 350? Well, because you have to. It's mandatory, right? But joking aside, you really want to understand this course because it's a kind of like a basis for all the courses that are coming in the software engineering side of your studies in fourth year and beyond when you probably do a master if you want. You do a master. So you might end up designing a real-time operating system. So this course in that case is definitely for you. You might end up not designing an operating system from scratch, but might end up designing parts of operating systems. So again, this course will come handy in that case. And you know, after all of you probably who are doing computer engineering, you are going to code and you're going to use the operating system. So knowing how things work under the hood and being able to efficiently use the capabilities that operating systems provide is something that you want to get out of this or to take out of this course. Now let's talk about important stuff. The first, let me go. Yeah, okay, so there is going to be a 30% on the final in-person exam. Labs are going to have 50% weight and quizzes are going to have 20% weight. For the labs, we'll have 3 labs. We will soon publish the lab manual on GitHub, and I will include a link to this, to the manual on the website. So there are 3 labs. So now I can probably answer the question that somebody asked. From which book do we need to read from for the labs? So everything will be in the lab manual. So there is for section 1, you will have to read a chapter of the second book, the first optional book. There will be 9 quizzes during the term. We will pick your 7 highest grades. So 2 quizzes you know will not consider your lowest grades. All the quizzes are going to be online. Quizzes are open source. You can consult your textbook, any resources that are available on the website. You can read the slides, everything. You cannot search Google or use other resources. So you're basically constrained to what is available on the website. You cannot communicate with anyone, your mom, dad, you know, friends, classmates, teammates, and none of that from other universities. No, it's you and you by yourself. But you can communicate with us. So we will publish the quizzes. Hopefully, we'll do our best at some point so that you have at least 2 to 3 days to sit and do the quiz. The quiz itself should take you 10-15 minutes. So once you take the first and second quiz, you probably lose any stress that you might have. So these are true-false questions. It will take like 10 to 15 minutes of your time. And the purpose of the quiz really is for you to look at the slides. That's it, to know what we have been talking about, that we're teaching. So quizzes are extremely easy, and they're open source, and they don't take time, 10 to 20 minutes, and it only has 20%. So take them easy. Don't be stressed out about them. There are sample examples online on the website, so you could be prepared. And that's it. So I'm getting a lot of questions. I'm going to keep them until I'm done with the admin part of the introduction, and then I'll answer all of them that I haven't probably talked about. Okay, so let's move on. There's a contingency statement here. Things might change as did. So we were supposed to do this in person, and here we are doing it online. This, you know, for now we are told that there will be an in-person final exam, but that might change. If that changes, then we will have to move weights around. The way I'm going to move it around, so I'm telling you upfront, is that the 30% that we put on in-person final, 20% of it is going to go to the quizzes. So quizzes become 40%, and the lab project becomes 60%. So that's, I'm telling you upfront, that's for now my contingency plan, unless something more crazy happens and, you know, quizzes get canceled or labs get canceled. But in case that only in-person final gets canceled, then here's how we're going to move the weights. Okay, now for the lab project, you're going to be designing a real-time operating system. We call it a real-time executive on DE1 SoC boards. You will connect to them for now through remote desktops. More details about that comes tomorrow during the tutorial that your lab instructor is going to present. So I'm going to leave it to him. So this slide is kind of messed up, but here are the important deadlines for now. So you have to form groups. Groups have to have 4 members. 5 is not allowed. 3 could happen, but just needs justification. We really want every group to have 4 members if possible. And you can actually sign up for your groups on Learn. It's set up right now. It's a self-enrollment. Last time I checked, a lot of people have already done it. If you haven't, do it. So it's on Learn. It's, you can just self-enroll in the groups. You are allowed to do 1 split up only. So if that happens, there are details on how this will happen in the lab manual. So I leave that to you to go and read. So basically, let's say you decide in the middle of lab 1 to split, you can't. So you have to finish lab 1 and then split for lab 2. And the other thing is that if you split, then every member of the group will lose their split up points, which you will see how much it is. So this incentivizes you to choose wisely which groups you want to be a member of. Here are the tentative weights that we're putting on different labs. So the group sign up has 3 points, 3%, and the deadline is January 11th at 23. P1 has 27%, P2 has 35%, and P3 has 35%. These are tentative. Again, if something crazy happens, we might have to move weights around. we'll definitely make sure to do this by cooperating with your representatives and the faculty of engineering and the department. One thing to note here is about your feedback. So this is very important. Right here, the first time I taught ECE 350, more than, I think it was fall 19 or fall 20, we had 5 labs. The second time I taught it, I reduced it to 4 labs. And then last time, I mean, the spring I taught it, but I took over somebody else because of their health issue. But this is the 3rd time I'm actually starting it again, and it decreased to 3 labs. And this is all because, excuse me, because of the feedback I got from students. So don't underestimate your feedback. The fact that this is 3 now is because of the feedback other students gave me. So you are benefiting from their feedback. So please provide feedback to continue this chain and benefit others that are coming after you. Okay. I guess here is a good time to take questions. So let me see what questions I have. Okay, I start from the top. So are quizzes timed? Yes. So as I said, you will have 3 days to take the quiz. The moment you start the quiz, you have about an hour. That hour is more than enough because it should take only 10 to 15 minutes. Okay, so we published that. Did I publish? Okay. Oh, I published 2. No. Okay. Okay, so the other question, do we need to read the textbook? You don't need to, but it's good if you do so. Everything will be in the slides. But if I do a terrible job in explaining, or if the slides are not enough, then you probably want to read the book. What is the quiz format? And that I think I answered. It's true, false. Do we need to pass the final to pass the course? No. Do we need to pass the final lab to pass the course? No. Okay, I answered all the questions. Good. Let's continue. Okay, so I have a bunch of slides for this lab. Now, previous labs that had 4 projects and 5 projects really were heavy, and people really cried their hearts out. This might be, yeah, I probably will show you how many hours people put in lab 2, just to give you an idea. It was, I think, about 40 hours per lab member. And you still have lab 2, so I haven't dropped lab 2. But it was about 40 hours per lab, per group member, not total. So people, the labs in ECE 350 are similar to labs in SE 350. So by the way, I'm actually teaching SE 350 as well. It was at 3:30, so it was, so sorry. When did it start? 2:30, so 2 hours ago. The first lecture of SE 350 was done as well. Excuse me. Both SE students and ECE students, probably majority of them will tell you that ECE 350 labs and SE 350 labs are the most time-consuming and difficult labs that they have had during their studies. And that probably is true. But at the same time, they're also very rewarding. One thing to note is please start early. Start early. This is really important. We software engineers and computer engineers usually say, oh, I have time, I'll do it later. But usually that's not true. So start early. So there are 2 ways to you're going to have groups of 4. You have to divide the work. You can divide functionally, or you can divide tasks. You can read more about them in the slides. I'm going to actually fast forward this portion. It's kind of like a bunch of suggestions to make the experience less painful or more rewarding, whatever you want to say. But I personally like the task division better than functional division, but be informed which one you choose and how you divide your work. Please communicate. Communication is key. I know that it's hard now that everything is online. We're not going to see each other, at least for a while, but still communicate. Communication is key. I'm going to fast forward, coordinate. So in the past, I would force each group to have a coordinator or a manager that students have to announce that this guy or this lady is basically our manager. But it was kind of like complicated to the admin stuff about it, so I dropped it. But I'm suggesting that you have a project manager or project coordinator for your group who would basically communicate with everyone, coordinate, and it saves you a ton if you have one. So give each other a break, because mistakes happen. I've seen projects where a group spent 10 hours debugging something because someone dropped K underscore from a function. You will get to know this bug very well pretty soon. But, you know, mistakes happen, and some of them are costly, especially time-wise. You know, don't go from somebody doing a mistake to cutting them off from everything and, you know, putting all the blame on them, or wanting to split up the group. First of all, if you do that, you're going to lose points. But secondly, it's not a good practice. Try to find out how you can get around mistakes that happen. One of the ways to minimize mistakes is to document. Now, if you go with the task division or functional division that we talked about, you know, each person is probably going to work on a piece of code. Now, at some point, you're going to join all that code, merge all your branches, and somebody else wants to read your code. It's really hard if you have no documentation for your code. So commenting is the basic thing you can do. You can actually write down your ideas. Your lab coordinator, your group coordinator can, you know, have a online whiteboard for everyone to write their ideas or write any details that they assumed when they were implementing a function or whatever there, so that everybody can see. So this is an important piece. Please, earliest first. You know, earliest start is the first important message, and coordination is the second important message. Documentation is the third important message, or suggestion, if you wish. So again, I'm going to just jump over these really quick. The fourth one that I strongly suggest is testing and continuous testing. As I said, time will come where you're going to merge your code to the master branch, and all of a sudden errors are going to pop up. Chances are. So if everybody has tested their piece separately, and when you merge, you have good tests, and you're doing the merging, you know, continuously, and the tests continuously. Don't wait until an hour before the deadline to merge, because it's not going to work. So merge test continuously. so that you don't get stressed out, and you don't have to have late submissions. Okay, so a little bit of administration, and this is the end of it. You will have 3 grace days without any penalty. After that, after you consume your 3 days, you're going to get 15% per late days. There is no, everything will be rounded up to a day. So if you are late 5 minutes, 10 minutes, 20 hours, 23 hours, they're all going to be rounded up to 1 day. So anything after the deadline is 1 day, and everything after 24 hours is 2 days, and everything after 48 hours is 3 days, until we hit the 72 hours mark, after which we don't accept your submission. So you only have 3 days, 3 late days per project, and 3 grace days in total. Okay, now a little bit about collaboration policy. So you can explain concepts to somebody else from another group. You can discuss algorithms and test strategies, with other groups. You can help people debug their codes only if your own code works and you're done. So you can't go and debug somebody else's code when your own code is not working. And you can search for online generic algorithm, like how to implement a hash table, for example. However, you cannot share code with anyone or your test cases. You cannot host your code on GitHub publicly. Even after this term, even after we're done with this term, you should not publish your code. You cannot copy or read somebody else's code for the purpose of getting ideas. Or you cannot copy or read somebody else's code from previous years. So these are all. This is the collaboration policy we have, and we really have. We should have zero tolerance policy for plagiarism. If we find any, and believe it or not, we have access to decades of code from SE 350 and the past 3 offerings of ECE 350. So we have enough code from previous years and your own submissions. We're gonna run MOS, and if we find any, unfortunately, you get 0 for that lab, and probably there will be penalties from the office of the associate dean. Okay, so if you have questions about the labs, please use Piazza, public or private questions. Try to avoid individual emails unless necessary. And then, as I said, office hours, how to book them, the link will be provided soon once I set up the office hours. Now, your very near future deadline is January 11th at 12:30 p.m. to set up your groups, to sign up for your groups. So that's pretty much it. Please work hard for this course. It will require you, unfortunately, to work hard. I'm in advance sorry for that, for all the pain you're going to go through this term. But hopefully it is rewarding, and hopefully it will be helpful to your studies. But at the same time, also find the time to relax even harder. Okay, so let me answer questions that you guys have asked. Okay, do we need to pass the lab to pass the course? That will depend. I mean, we don't have individual thresholds for you to pass the lab or pass the quizzes or pass the final exam. In total, your total should be above the threshold that university has to pass the course. So each individual component doesn't have a threshold, if that's what you're asking. What programming language is used in the labs? It's C. Can we take generic code from online? Yes, if it is really generic, like a hash table or queues, yes, you can. If policy 71 is violated, do the entire group gets punished? It would be case by cases. So if one member did it without anybody else knowing, then that one member will get punished. If the entire group was aware of it, then the entire group will be punished. So it will be case by case basis. Around how many weeks are we given to complete a lab? That's a question that you can get an answer by looking at the schedule. So if you look at the schedule, you see the deadlines. So this is lab 1 deadline, which is going to be on February 1st. So from now until February 1st. And then about a month later, you have lab 2. This is the one I told you that takes about 40 hours of your time, probably, or even more. And then lab 3 is about a month after that. So almost a month for each lab. But don't count on that. That's very, very deceiving. Do not count on it. Okay. Going back, I don't know what's going on with my throat. I hope I'm not destroying the experience for you. Okay. Let's just start with the meat of the. I mean, for some of you, the meat of the course was what I just presented. But let's just start talking about real-time operating systems. I'm going to start with defining what a real-time system is, and then we move on to defining operating system. I got another question I will answer later after I'm like midway through this part. So. A real-time system is a system that has a temporal aspect to it. So usually the systems that we build have a functional aspect. We want it to function well, do what it's supposed to do. Now with real-time systems, on top of the functionality that we expect, we also have some timing constraints. We want to do what we want to do in a timely manner. So it's usually specified by deadlines. We say that your system has let's say 30 microseconds to finish this task. And usually these real-time systems, you can find them in embedded systems. Usually, not all the time, but usually in embedded systems like safety critical systems, like satellites, right? In medical devices. So these are the ones that are usually real-time system with timing constraints. And when you design an operating system for a real-time system, you have to consider this aspect of your system. So the operating system has to be aware of this timing aspect and has to support it, which is basically what we're going to talk about in this course. Now, the types of operating systems, the real-time systems, based on the deadline, we have 3 types of real-time systems. Excuse me, let me have a big cough. Let me mute myself. Actually, I'm going to go grab tea. So give me a second. I'll be back in a few seconds. Sorry about that. Yes, I'm okay. I'm okay. Okay, so I'm getting a lot of stuff, so I will respond again at some breaking point. Okay, so we have three types of real-time systems: soft real-time systems, firm real-time systems, and hard real-time system. So let's say I have a task, and the task has a deadline. In a soft real-time system, so this is the deadline I have for my task, D. If I finish my task anytime before the deadline, I'm happy. I get the this is the value I get from doing it. When I miss the deadline, the value I get from doing this job decreases until at some point it becomes zero. So if I do the task or I don't do the task, it doesn't really matter anymore. So I basically missed doing this job. But it's not a harsh punishment if I miss the deadline. The value decreases and then eventually gets zero. In a firm real-time system, if I do my job before the deadline, I'm okay. So it's okay. Anytime before the deadline, I finish my job, I'm going to get the value. The moment I hit the deadline, if I finish, it's as if I didn't do the job at all. So I get zero value from doing the job after the deadline. Now, this is even worse in hard real-time systems. In hard real-time systems, anytime before the deadline you do the job, D1, D2, until your actual deadline, you're fine. You get the value out of doing the job. The moment you hit the deadline, if you haven't finished, you're going to get negative value. So you're going to be harmed. For instance, you can assume, if it is a satellite and you don't make the decision that you have to do, you don't take the action in the timely manner, like millions of dollars are wasted because the satellite maybe like explodes. Or if it is a medical device and a life is lost, then you get negative reward for what just happened. Or if it is a self-driving car and you didn't hit the brake in the timely manner, and now there is an accident. So these are the hard real-time systems. Now, in a spectrum of hard to no real-time system, so you can basically put them like this. So no real-time requirement, hard real-time, and in between soft. And here I have a bunch of examples, like an electronic engine or a reactor here, for example. Reactor or a satellite would be here. Flight control is kind of like a hard real-time system. And then you have these, telecommunication, cruise control, internet, video and audio. These are kind of like soft real-time. If you get, a frame after the deadline, it's fine. Like the user experience is not going to be that bad. After a while, it would have been as if like you didn't do it. But then you have these systems like a computer simulator or a user interface. These systems aren't really real time. They're not much deadline into them. Okay, now that we saw what real-time systems are, let's talk about what an operating system is. So in reality, there is really no universal definition of an operating system. If you really point a gun to me and say, no, you have to define operating system, I would just say whatever is shipped with the operating system package you download or you buy. Like, let's say you buy a Windows system or you get your Mac. Initially, what you have is sort of an operating system, or you download an Ubuntu image. This is a result of having two lectures back to back. So Poor you guys, you're going to deal with this during the semester. Okay, so that's if you want a definition. Now, the one that I prefer, if somebody asks me what is an operating system, is instead of giving them one sentence what an operating system is to define operating system through what an operating system does. So what does an operating system do? And then we just look at different components in our system and we say, okay, this component does what an operating system should do. Therefore, this component is part of operating system. This other component is not doing what an operating system should do. Therefore, this component is not part of the operating system. So I think that's the best way. So now in the coming slides, I'm going to just talk about what an operating system does. In a really high-level overview, you can say operating system provides an abstraction. So it abstracts hardware to software, to applications. So it sits between hardware and applications. So you have your hardware and you have your applications. Operating system sits in between, hides the complexity of hardware to the applications by providing an abstraction. In the meantime, operating system also protects applications from each other. Basically isolates application, doesn't let one application to corrupt another one. Better call these processes. So isolating processes. On top of that, operating system should provide security, authentication, privacy, and all the good other stuff for the processes. It's basically operating system is your system manager that has to do all the good stuff. Now, if you talk about communication, if you talk about isolation and protection, you might say, okay, so this process 1 and this process 2 are isolated from each other, but what if they want to talk to each other? So you probably have seen the ways that you can program two processes to talk to each other, inter-process communication. Now, in this course, you will see how that would be implemented in the operating system. How does the operating system allow two different processes that are supposed to be isolated talk to each other? So that's another thing that the operating system does. Now, if I want to categorize what the operating system does, I can categorize it into 3 categories. The first category is the kind of jobs that operating system do to be an illusionist. What do I mean by that? This is basically the abstraction layer that we talked about. It's kind of like you're hiding whatever is in the hardware from your software. You're kind of like an illusionist. You create this illusion for your process that it really doesn't know what processor is in the system, or how much memory you have in the system, or if you have caches or not, or if it is an SSD or if it is a hard disk, or if you have a 10 gigabyte memory, 10 gigabit per second network card, or a 100 gigabit per second network card. So the operating system sits in between and creates this illusion for the applications that they have, for example, infinite amount of memory. So whenever you're writing your application, you usually don't think about how, if the system that is going to run your application has 2 gigabyte of memory, or 3 gigabyte of memory, or 4 gigabyte of memory, or 32 gigabyte of memory. Unless you're doing some performance stuff, you usually don't care. So from the process point of view, it's as if like it's running on a dedicated machine. So let's dive into this piece. Let me look at the questions posted to see if. Oh, I will answer. I'll answer the question. Sorry. So let me go and finish this illusion part, and then I'll come back and answer the questions that you've asked. Okay, so I have this big box here, written hardware. So I'm going to put stuff inside. Let's start with the softwares. Software, we're going to just look at a running program. Let's say you have a running program. What comes in the hardware part? Well, the most basic thing is that you need a processor to run your code, and then you need memory to store your data. Now, probably this memory is, divided into what is needed for the operating system and what is needed for each one of the software or processes that are running. Now, let's add a little bit more details. Your processor has a bunch of registers, and this is basically the butter and bread for the processor to do arithmetic, for example, or to do whatever it does. It needs those registers. So we're going to bring data from memory to these registers to do processing, to do execution. Now, we probably want to make it faster, so we're going to add a cache there. And as you will see in the course, you probably want to make it even faster by, when you add virtual memory, you want to make the address translations faster. So you have to add some other types of caches like TLBs. You have to add page tables. Apart from the processor and memory, you have other hardware. You have the storage, for example, your SSD or your hard disk. You have your display. You have your network card. You have your GPU, for example. You have your keyboard, your USB devices that you're connecting. So all of these come in this under the umbrella of hardware. And inside the hardware, we kind of have to have them all connected to each other, right? We want, maybe the application wants to store something in the SSD, or maybe the application wants to communicate through the network. So we have to connect all of this, kind of like we have to put a bus there and then control all the communications between different components. Now, what is the interface between hardware and software? This interface is instruction set architecture, like x86 or ARM or IBM Power or RISC-V. So this instruction set abstraction tells software what is available in the hardware. But is it safe to allow software to interact with this ISA in an unprotected manner? And the answer, as we will soon see, is no. We don't really want to allow software to directly access the hardware. So what do? So we put an operating system in between. So on top of our hardware, we're going to put the operating system. Now, operating system, as we talked, we're talking about the illusionist. So it's going to provide abstraction. How does the operating system provide abstraction for the process? For the processor, it's going to create the abstraction of threads, which you probably have seen in ECE 252. What about memory? This is going to be the virtual address space. What about storage? This is going to be your file system. What about networking? It's going to be the sockets. So these are the abstractions that operating system provides for the software to hide the details of and the complexities of the hardware. Now, operating systems run processes, as you have seen before, and processes basically use these abstractions. Process itself is an abstraction for for running a program. But through these abstractions, threads, addresses, spaces, file systems, sockets, the process uses hardware. What is the second kind of job of an operating system? I actually promised to answer questions. Let me answer the questions. Okay, so when you set 40 hours per person for lab 2, is that the expected time it would require, or is that just an exceptional case of one group taking a lot of time? So I did winter last year. Winter 20, after each lab, I would put a pool asking how many hours it took you to complete the lecture. So I'm going to share those with you this term. And for lab 2, many, it took them more than 40 hours. So let's put it that way. Although I have to say, with lab 2, so winter 20, we had 256 students, and we only had, I think, 25 to 26 boards, and it was an online term, so they had to, connect through remote desktops. So there was a fight to get access to the boards. So that also contributed to this 40 hours. So many of this time was people waiting to get access to the boards. So for what it's worth, take that into consideration. It's not how much the lab requires. Usually, I also would ask them to break it down what took them the most time, and it almost unanimously was debugging. So as you will see, you're going to see assembly code inside your C++, inside your C code, and usually that's hard to debug. And silly mistakes take hours and hours to find. And so most of this time is debugging. It's not really 40 hours of coding. It's usually probably 5 to 10 hours of coding and then 30 hours of debugging, if you wish. Okay, so let's move on faster. Publish. Are there operating systems that are not real-time? Yes, of course. Ubuntu, for example, is not a real-time operating system. Although it has some support for real-time tasks, especially when it comes to task scheduling and job scheduling, but it's generally not considered as a real-time operating system. Sir, are you okay? I think you might want to get tested. Oh, it's not COVID. Yeah, it's talking. Okay. Or it might be COVID, who knows? Hopefully it's not. Okay, so what kind of tea are you going to be drinking? It's a black tea. Very tasty. No sugar. Okay. After what lecture should we be able to start each lab? That has been considered when we were planning. So immediately after you're done with lab 1, you can start lab 2. Immediately when you're done with lab 2, you can start lab 3. Right now, after you have a group and after we publish lab 1, you can immediately start lab 1. Can you give examples of when you would want each type of, I assume, real-time systems? So it really depends. When you're talking about hard, soft, and firm real-time systems, it really is exogenous. It's not like we choose one system over another. It's kind of what is required of your system to do. If you're designing an operating system for a satellite, you have to consider it as a hard real-time system. Maybe there are soft real-time tasks there, but mostly it's a hard real-time system. So it's a requirement of the system. What does the environment want that makes you choose what kind of system you want? So, if missing a deadline is detrimental and has cost, then it becomes a hard real-time system. If missing a deadline means that you have to throw that task away, it's a firm real-time system. If missing a deadline means that you still have a little bit more time, I'm not going to be that happy with the result, but I'm still happy. Just try to finish it as fast as you can. Then you have a soft real-time system. Okay, so another question. So failure is signified by a negative value of usefulness. So I would say failure in meeting the deadline. So again, you have to consider that you have the functionality. You first of all have to finish the task correctly. If it is a 2 + 2, you shouldn't return 5. But then the second thing is that you should return 4 in a timely manner. And if you don't do that, let's say I needed you to activate the braking system for the car to stop, and you only had 50 microseconds to do this. If you didn't, and you missed the deadline, now I have an accident or somebody was killed. So it's a hard real-time system. So because there is a harm being done. Now, if you had 50 microseconds to download a frame, if I'm streaming from Netflix, and you didn't, then okay, so 1 frame was missed. I still doesn't change my experience as a user of this system. I'm still watching my stream, like even 100 or thousands of them are missed. It's okay. I'm still watching. So then you have kind of like a soft real-time system over there. Okay, after what lecture can we start lab 1? You can start lab 1 immediately. So once the manual is released, you can start doing the labs. Okay, how much time do I have left? 20 minutes. Okay, so the second job of an operating system is to act as a referee. Let me see how many slides I have. Okay, we're a little bit behind. So the referee kicks in when there is competition for hardware resources. So that's where the operating system should come in and say, you get this, the other application gets this, the other process gets that. So operating system has to come in and decide who gets access to what. So here is an example. Let's say I have 2 processes, process 1 and process 2. I have their data in memory. And let's say at this point I'm running process 1. So the registers now get their values from a memory location for process 1. Now let's say I context switch. So this is the first part that operating system kicks in as a referee, says, okay, process 1, you're done with using the processor. I'm going to give the processor to process 2. So this is a referee coming in and saying, okay, process 2, you now go get started. Now, let's say process 2 wants to maliciously access the memory region of process 1. Or maybe it wants to access the OS memory. Or maybe it wants to have a direct and unprotected access to a storage. So here is where the operating system comes in and says, no, you can't access this. So this is kind of like an access control, kind of like a protective. It's the referee coming in wherever you're going to access the hardware and says, no, you're not allowed to do this, or you're allowed to do this. Go ahead and do this. Now, if you want to, be a little bit more precise, this is a protection boundary. This red line here. And so anything up here, we kind of, I have to say, kind of give direct access to processes, and anything here we prevent. We kind of allow direct access, and here we prevent direct access. If you want to, to get performance, you don't want to interfere with every single instruction that your application is running on the processor. So you kind of allow the application to run directly on the processor. That's where you get the, if there's an add, a multiply, a division, loading from memory, accessing memory, reading memory. So you kind of allow the processes to access processor and memory kind of directly. There is some indirection. For example, your application cannot run certain instructions, which we will talk about, right? They cannot, for example, disable interrupts. So there are certain instructions that you don't want the application to run. But other than that, you allow the application to run kind of directly on the processor. Also with the memory, if application wants to read or write from its memory, you kind of allow it to read and write from memory, whatever it wants to read and write. Again, you want to restrict this access. You don't want them to access, for example, somebody else's memory, but their own memory, you kind of allow them to directly access. But anything other than that, like a storage SSD or the network or the display, you're going to say no. You're going to go through the operating system. And this is where the system calls come in. Like you open a file, the open system call, the read system call, the write system call, the sockets, the entire sockets system calls. Or for example, for the display, you want, for instance, to access the display. You go again through the operating system to access the display. Although there is a little bit of difference when it comes to the display, which we will talk about when we talk about the third job of the operating system. Now, the third one is a glue. So we want to provide a common framework for all the services. And we're going to do this through this two components. One is the system libraries. For example, when you do printf, it's kind of like you want something to be displayed, for example, on the display. Or the windowing system. You want to open a window, close a window, maximize a window, minimize the window. You don't want every single application to write their own windowing. Or battery management. I guess I have a slide for that. So that's how you're allowing your processes to access different hardware that you want them to be protected through a common service, common thing that kind of glues everything, provides a unified abstraction. And that's, again, through these system calls, system libraries, and system calls. For example, as I said, windowing, or maybe you have a battery. You don't want each process to manage its own energy consumption. So you kind of have a power management component in the operating system. Overall, the bottom line for an operating system is to run applications, run processes, and run them as fast as possible, and to be incidental, meaning that you don't want operating system to consume resources. You want operating system to allocate resources. If operating system consumes all the resources, there is nothing more to be offered to the application. So you want operating system to kick in when necessary, do minimal thing, get out of the picture, let the processes use the resources available. In this process, the operating system usually relies on the hardware. Usually. The reason that operating system relies on hardware is for performance, mostly. As we will see, I will make sure actually to highlight this point throughout the semester. Whenever we talk about certain method or certain algorithm or certain mechanism, I'm going to say, okay, look, here we're using hardware, but it's not necessary. The software, the operating system can do it by itself, but the cost of that is time. So it's going to degrade the performance if the operating system wants to do it. One example, for example, is the segmentation fault that you saw. So if for each access that your application does to memory, You want the operating system to wake up and say, oh, this access was allowed or this access wasn't allowed. Then the performance will be terrible. It will take ages to run a Hello World application. Instead, we're going to delegate this checking to hardware. So operating system is going to go set some flags, set some registers, say, hardware, the next application that you're going to run has access to this memory. So make sure that it doesn't go out. Now, if the application goes out, hardware checks and goes and wakes up the memory and says, oh, memory, wakes up the operating system and says, oh, operating system, this application, this process accessed some memory that you told me it's not supposed to. So what should I do? And at that point, operating system wakes up and makes a decision. Maybe it was okay. Maybe something should be done. Maybe it was not okay. It's a segmentation fault, and so on and so forth. So this is where we're going to rely on hardware just usually to get performance. And there are a bunch of examples here. Memory management, dual mode operation, interrupts, traps, and so on and so forth, which we will actually talk about all of them or most of them in details in the future slides or future lectures. This point I want to actually emphasize. This is very important, at least to me, that you have to note that the hardware is evolving, and so should the operating system. Unfortunately, there is this misperception that, okay, we have Linux and Linux is working, and why should we even care about operating systems? At the end of the term, I will post a keynote talk from OSDI 2020, I think. And there you will see how Linux is failing to really keep up with the new hardware. And we will see how detrimental it is, this perception that people have that, oh, Linux is going to take care of it. Now, it is a golden time for hardware designers. As you can see, there are everyday new hardware comes out, new types of accelerators and TPUs and new GPUs and all of that. New compilers are coming up as well. But so should new operating systems that consider that the design of the hardware is changing. Unfortunately, we won't have time to dig into those new hardware and what is needed. So this course gives you basics of operating system. Now, if you're interested, and I hope that some of you are interested, we need more students. The fact that you're taking this course in third year doesn't mean that it's like less important than the elective courses that you're going to take in fourth year. It's actually not true at all. This is a really important course, and not only it is a basis for other courses, but also itself is an important topic for new generation of operating system designers to come in and really rethink how operating systems are designed and how they're implemented. So keep that in mind. So the hardware is changing, and so should the operating system. Okay, so to put everything together, what do operating systems do? They provide abstraction, they manage devices, and they implement different methods using different techniques and implementations. I got a question I will answer hopefully before the end of the lecture. Okay, so unfortunately, this is the only time we're going to talk about virtual machines. Unfortunately, I won't have time to dig deeper into what virtual machines are, but it's important, so let's talk about them. And they're very related to operating systems. So virtual machines are software that emulate hardware. So that's basically what they do. They create an illusion for whatever runs on top of them that they're running on a bare metal hardware. Now, there are three types of virtual machines. There is the process virtual machine, there is system virtual machine. Sorry, there are two types. I made the same mistake 2 hours ago. But there are two: process virtual machine and system virtual machine. Let's look at their differences. So process virtual machine runs processes, obviously. So it kind of, so this figure shows it all. So you have your hardware that provides an actual ISA. Now your host operating system runs on top of it and provides an ABI, application binary abstraction, or interface, sorry. Then you put your virtual machine here, and your virtual machine provides virtual ABI and virtual ISI to your processes. So the process that is running on this virtual machine doesn't necessarily know what the ISA of the hardware is, or what the ABI of the operating system is. So one example of this is Java virtual machine. So if you have a Java code, you can run it on ARM, you can run it on x86, you can run it on potentially RISC-V, and all of them, they're running on top of Java virtual machine. So they are platform independent. So your Java code, your Java processes are virtualized, and that would be basically process virtualization and process virtual machines. Another example is .NET Framework. Now, another type of virtual machine is what is more, famous or maybe more practical in today's data center world, and that is actual system virtual machines. Now, the process virtual machine runs processes. System virtual machines run operating systems. And to do this, they need help from a third party called hypervisor. Now, there are two types of hypervisors. There is the type 1 hypervisor and there is type 2 hypervisor. Now, all hypervisors manage VMs. They have to know what the state of the VM is. Is it running? Is it halted? Is it terminated? What is the state of virtual machine? What are the resources that it's using? Now, the difference between type 1 and type 2 is how they allocate hardware to the virtual machines. In type 1, that you can see here, so you have your hardware, and on top of that, you run your hypervisor. So hypervisor not only manages virtual machines, but also allocates hardware to them. So it's kind of like arbitrary how hardware is allocated. In type 2, however, the hypervisor runs on top of the host operating system. So it relies on the operating system to provide hardware allocation support. Examples of type 1 are Xen, VMware, ESXi. Examples of type 2 are VirtualBox, VMware Workstation, and KVM. Now, some of you probably have worked with and have seen containers. So what are the containers? How do you compare them with virtual machines? Containers are not providing full machine virtualization. So VMs kind of create this illusion that whatever is running has an isolated machine for them. In contrast, containers create an illusion that you have an isolated OS, operating system. So they don't simulate or emulate the hardware. They create virtual operating systems. So when you have a VM, it's as if you have access to a server of yourself, the entire hardware. But if you have a container, it's as if you have access to your own operating system. Now, containers rely on host operating systems to create this support. For example, they rely on Linux C groups, namespace, etc. And And you can usually run your containers under either on bare metal. So if you have a Linux container and you have a Linux system, you can just run it on your Linux system. If you want to run a Linux container in a Windows operating system, then you probably want a virtual machine first. So you want a virtual machine that virtualizes Linux on Windows, and then you can run your Linux container inside that virtual machine. So you can run it basically on bare metal or inside a virtual machine, your container. And there are two types of containers. So there is an OS container and there is application container. OS containers basically run multiple applications, whereas application containers like Docker, they are expected to just run one application. So by making this assumption, they actually get more performance, that they're just going to run a single application. Sorry, I went over time. So I apologize. It's 5:51. I'm going to answer the questions. For those who ask, I have two questions. The rest of you are free to go, but let me answer the question. So the question is, so all the examples mentioned can be done without hardware support. I don't want to say all, but most of them. And I will make sure that during the term, whenever it comes, I will highlight that this functionality could be done in software, but we're doing it in hardware for performance. So I will make sure to mention this as you know, different topics come up. Okay, another question. Are these lectures going to be posted on Learn? These, I explained at the beginning, these lectures are recorded right now. And after the lecture, you can actually access them using the course website. So the same link that took you or brought you to this online lecture, you can use it to watch the recording after I end this live stream. I also post the videos, the recordings on YouTube later on. Okay, so it says each VM has an illusion of running on isolated machine. Does this include process VM? Sort of, yes, yeah, because even with process VM, the process thinks that it has its own hardware. So the Java virtual machine, for example, is emulating sort of the hardware as well. Although this emulation depends on the operating system, so it's not done completely by Java virtual machine, but it's done through that. Whereas in containers, so if you have a Linux container, for example, or if you have an x86 container, you cannot run this on an ARM machine. So that's the difference, right? An x86 container cannot run on an ARM machine unless you first run a virtual machine and then run your container inside that virtual machine. Then you can do whatever you want. But plain, like, your container cannot, like a Linux container cannot run on a Windows operating system, again, unless you have a virtual machine. Okay, so a sandbox is a type of container too. Basically, what I mean by sandbox is how you virtualize an operating system. So it kind of creates this sandbox that you have your own operating system. That's what I mean by sandboxing. What the advantages of having an isolated OS versus full VM? Full VM gives you a lot of flexibility because you can virtualize Linux on Windows, you can virtualize x86 on ARM. It's unlimited, so things that you can do. However, it comes with a cost. So you have a performance cost. When you have VMs, there is cost because you're emulating the hardware. So the hypervisor kicks in usually very frequently to do the emulation. So the performance is really bad on VMs. However, in containers where you're just emulating the operating system, it's as if you're running on bare metal. So there is a little bit of extra cost, but most of it is on bare metal because you're not emulating the hardware. The application is written for x86 and your system is x86 and there is no emulation. So there is only a little bit of, that sandboxing that I said that adds a little bit of cost. So containers are much faster than virtual machines, but then they're less flexible, right? You can't, have an ARM container on an x86. Again, unless you have a virtual machine that runs your container. Okay. Then I have a question. Will you finish these lectures slides during the next lecture, or are we expected to go through them on our own? I'll try to finish them next time. Okay, so thank you for those of you who stayed even 6 minutes after the end of this lecture. Thank you for those of you who will be watching these lectures. Take care, be safe. We'll see you again on Tuesday. Bye-bye.